In a mass screening program, a new diagnostic test is being used to detect the presence or otherwise of a certain disease. When the person being tested has the disease, the test gives a positive result with probability 0.96. When the person being tested does not have the disease, the test gives a positive result with a probability of 0.01. It is known that 2% of the population have the disease. The test is given to a randomly chosen member of the population. We want to find the probability that a positive result is obtained. So what we're looking at here is a typical tree diagram question. We have two events. One event is dependent on the other. The initial event is whether a person has the disease or not. So what we're going to do is that we have two branches. One for if you have the disease, one if you don't have the disease. It tells us that 2% of the population has a disease, so the probability of having the disease is 0.02. That means the probability of not having the disease is 0.98. Now, we're told next the population is tested. So the second stage is this test. So you can either come out with a positive result or a negative result. So probability that it's positive, given that the person has the disease, we are told is 0.96. This means the probability that it's negative, given that the person has a disease, must be 0.04. When the people who don't have the disease are tested also, we have the same situation. So we could have the probability that the person has the disease, is tested positive, given that they don't have the disease. Well, the probability that you get a positive result here is 0.01. And that means then the probability that you have a negative result if you don't have the disease is equal to 0.99. So let's now look at the outcomes in these scenarios. So we can have the probability that you have the disease and you get a positive result. 0.02 times 0.96 will give us 0.0192. We could have the probability that you have the disease and you come out negative, which is 0.02 times 0.04, which gives me 0.0008. Probability that you don't have the disease, but you still get a positive result, will be 0.01 times 0.098, which gives us 0.0098. And then finally, probability that you don't have the disease and that you test negative is going to be given as 0.98 times by 0.99, which is an answer of 0.9702. Okay then, let's have a look at actually answering the questions now. So part A says, find the probability that we get a positive result. Well, here is one of our positive results where you have the disease and you test positive, and here is another positive result where you don't have the disease and you test positive. So these are mutually exclusive events, which means we are going to add them together. So 0.0192 plus 0.0098, and this is going to give us an answer of 0.029. Okay, so how are we getting the marks in this question? Well, the method mark and accuracy marks come from using the tree diagram. And so looking at these, we then get the accuracy mark for getting 0.029, and of course this calculation here is part of using the tree diagram. Part B. Part B says, given that the positive result is obtained, find the probability that the person has the disease. So what I'm looking to find is probability of a disease given a positive result. So this is then defined using conditional probability as the probability that the person has the disease and gets a positive result all over the probability of a positive result. So probability of disease and a positive result is 0.0192 over probability that it is positive, which is 0.029. This then gives us an answer of 96 over 145 if you've got, or an equivalent decimal when it's rounded. It's best to work with a fraction if possible. 3 marks for this part of the question. We get a statement mark if we get the numerator correct, we get a statement mark if we get the denominator correct, and we get a statement mark if we get the final probability or the rounded decimal version. So let's look at part 2. We want to find that given that the positive result is obtained, find the probability that a positive result will be attained if a second test is given to this person. So again, we're looking for a probability of a positive. The way we're going to do this is, if we consider first of all that the person tested positive and had the disease, we have this 96 out of 145. What's the probability that he will get a positive result again? Well, it's going to be 96 over 145 multiplied by the probability of a positive result given that he's positive, which is 0.96. But not only that, whatever this person has, we don't know whether we've got disease or not. The person could not have had the disease. So we need to then consider what happens if they didn't have the disease. What's the probability of them testing positive? So 96 out of 145, it means that we get 49 out of 145 is the probability they were negative given that they had a positive result. And so what's the probability of them getting another positive result? Well, it's that probability multiplied by the probability of a positive result again, which is 0.01. When we put this into a calculator, what we're going to get is an answer of 0.639. So 3 more marks being awarded for this part of the question. How do I get those 3 marks? Well, first of all, you get a method mark and an accuracy mark for identifying the correct calculation, and then we get an accuracy mark for getting this correct answer here. Really, we should be stating that this is to 3 decimal places. Okay, I hope that all made sense and that you understood it.